Hello, good evening. Today is April 5th evening, late evening, and I'm recording this presentation. This is Bhavani Thuraisingam from the University of Texas, Dallas. This is a recorded presentation for a talk I will be giving tomorrow, April 6th, live at New York Institute of Technology, NYIT. And this talk, of course, will be virtual, but I always record a backup presentation before I give any invited talk address or a featured or keynote address, just in case there is a technology glitch. So I'm going to start my presentation and I will share my screen. Right. So I believe it's a 1 hour presentation, but I'll be talking for about, I believe, 45, 50 minutes, and then there will be questions and answers. So what I usually do is record the presentation and send the Zoom link to the my host who invited me to give this presentation. And then I will, of course, be there live, but in case if there's a technology glitch, then I might listen in on the phone and then answer the questions. So that's the plan for April 6th, right? So this will be given, the live presentation will be given on April 6th, and that's going to be at 1 p.m., I believe, Eastern Daylight Time. That's 12 noon Central Daylight Time. Okay, so my talk is going to be integrating cybersecurity and artificial intelligence with applications in Internet of Transportation and infrastructures. Outline of my talk, going to be 3 parts. Part 1 is going to be, I just want to make sure that the sound is working. Oh dear, okay. So here's the outline of my talk. Integrating cybersecurity and data science, that's part 1. So I will be discussing 5 topics: big data security and privacy, privacy-aware quantified self, data science, machine learning, AI for cybersecurity applications, and then securing data science, because what happens if the machine learning data science techniques are attacked? And then I'll be talking about an area that I'm really getting involved is trustworthy machine learning and AI. So that's part 1. Part 2 is on security and privacy for Internet of Transportation and infrastructures. And then part 3 will apply part 1 to part 2. So while part 1 and part 2 are research based on research projects that's either ongoing or it's completed, part 3 is going to be our research in the future. So it's going to be some directions. And I'd like to acknowledge all of our sponsors and also my colleagues, Professor Alvaro Cardenas, Murad Kantajalu, Latifa Khan, and our former PhD student, Dr. Rolf Quanenes, and our project coordinator, Ms. Rhonda Walls. Okay, so part 1 is integrating cybersecurity and AI and machine learning or data science. So I'm going to use the terms AI, machine learning, data science interchangeably. So motivation, data mining, security, and privacy. So I believe I introduced this idea of data mining, security, and privacy at a keynote address I gave at the IFIP 11.3 working conference in database security back in 1996 in Como, Italy. So while I say I introduced the area, it was mainly the privacy aspects that could result from data mining. Data mining for security applications such as intrusion detection was already being investigated in the early 1990s by others as well as by us. I was at the MITRE Corporation at the time. And then later in 1998, I gave another keynote address at the Pacific Asia Knowledge Discovery and Database Conference. And then I subsequently published what I call a landmark paper And I'll tell you why I call it a landmark paper, right? While I was at the National Science Foundation as a program director in 2002, and this spawned a new area of research. The reason I call it a landmark paper is that when you are at the National Science Foundation as a program director and you are responsible for funding research and setting the direction, then it's, whatever you say, right? People pay attention. And so that paper had a lot of citations. It was published in CKDD. Okay, so then the privacy preserving data mining. How do you do data mining at the same time ensure privacy? So we did a little bit of work at MITRE Corporation, myself and my colleague, Professor Chris Clifton, who is now at Purdue. And at that time, the word privacy preserving data mining was really coined by the researchers at IBM Almaden Research Center, Professor Rakesh Agrawal and his colleagues. So the whole idea is to take the original data and then add noise. So you get some noise added data. So X becomes X prime. You modify the data mining process and then you get the final modified result. And so the end result should be the same, right? Even because once you do data mining, whether you do with the original data or modified data, the end result. So when the people who live in, say, Dallas, Fort Worth, Texas, there's a higher incidence of diabetes or maybe COVID or lung cancer. So because you want to know the final results. So when I joined University of Texas at Dallas in October 2004, my first PhD student, it was a lady, Dr. Lee Liu. And so I jointly advised her with my colleague, Professor Murat Kantajalu. And so she did some work on privacy preserving decision trees. And she also explored the perturbation method further, the perturbation method that was introduced by the IBM Almaden researchers. And so that research was carried out between, actually I say 2005, but late 2004 to 2008. And then comes big data, right? So data mining, security, and privacy is exacerbated with big data and data science. So I hosted an NSF workshop on big data security and privacy in September 2014 and presented the results to the interagency working group in February 2015. So my sponsor at the our program director at National Science Foundation, he wanted us to present these results for the interagency working group. And so that resulted in some efforts being funded. Okay, so what is big data security and privacy? So this was really some results from our workshop. So we know technological advances and novel applications. It's now possible to capture, process, analyze large amounts of security for various data for various tasks. These tasks could be security tasks like access control, authentication, anomaly detection, monitoring the user, protecting from insider threat, or it could be any other application in healthcare, in finance. So analyzing and integrating data collected on the web, one can identify connections and relationships among individuals that may in turn help with homeland protection, disease outbreaks, and so on. And this data collected, even if anonymized, say you can remove the identifiers in two records, right? Record A and record B. You remove the identifiers, but when you join the records, essentially link the records, you could re-identify the individuals. Maybe not all the time, but perhaps sometimes you could re-identify. And then once the person is identified, you can figure out all the properties, right? And so if that information is misused or stolen, it can lead to numerous privacy breaches. So that's one thing. So data, so if you look at here, right, lots of data being collected on the web, and so you identify the relationships and so on, and that can be used for homeland protection, cybersecurity, healthcare, finance, COVID-19, whatever, right? But these data analytics, right, not only sometimes privacy could be violated, but then these machine learning data analytics techniques could also be attacked. So if you are using machine learning for a variety of applications, and if these machine learning techniques are attacked, then it could be a disaster, right? So what were the directions that we proposed? access control models, and I'm not going to discuss that further. So we said, you have, it's lots and lots of data. So big data, 5 V's: velocity, I always get confused, velocity, volume, variety, veracity, and value, right? The 5 V's. And so you may need different types of access control models, then privacy enhanced techniques. And I'm going to focus on 2 things, 3 privacy enhanced techniques, and then how can we apply big data techniques, analytics for cybersecurity like intrusion detection, and I'll be focusing on insider threat. And then what happens if these machine learning techniques are attacked? And then we will focus on secure machine learning. Okay. So very briefly, privacy aware quantified self. This is a movement. So quantified self is a movement by sociologists, psychologists, right? So they came up with the quantified self movement. But before that, we are all carrying smartphones, right? So, there's lots and lots of data that's being collected in our smartphone, billions of users. Now with the quantified self, right, this movement, our smartphones can really help us, for better health habits. So for instance, when I open the refrigerator, by the way, I love vanilla ice cream and milk chocolates. But of course, I don't keep any of that in the refrigerator because that's too tempting. But let's just assume that I have vanilla ice cream. So when I open the refrigerator and grab the ice cream or the milk chocolates, then my smartphone, or there should be some message telling me, no, this is not good for you. You're not supposed to eat chocolates. You're not supposed to eat vanilla ice cream. Wouldn't that be great? But then what happens if all of this personal data is shared with various retailers and insurance companies? And then such data collection and sharing are often carried out without the user's knowledge. That's really poses grave danger to the user. So data collected by device monitoring, blood glucose levels could be used by an insurance company to deny coverage to a user and even the user's relatives. So if they find that, say, I have diabetes, then my son might be denied coverage, not only myself, but also my son. Fortunately, I do not have diabetes, or I should say yet. But still, right, that could be, very, very serious problems. Such privacy violations could easily get out of control if data collectors could aggregate financial and health related data with tweets, Facebook activity, purchase patterns, and then that could be, utter chaos, right? Data collectors and psychological and physical distress, all of that information could be misused. So to address these growing challenges, we need tools for privacy protection in quantified self applications. So we published a paper on this work at a very well-known conference, ACM SACMAT. And so we are proposing a policy-based, privacy-aware quantified self, right? And a data management framework. That framework will reside in our smartphone. So we get our health information, fitness data, location data, social media, image, audio, and so on. And all of that is collected. And I'll come back to that in a minute. Some of the data stored in cloud, and through cloud services, anonymized data, encrypted shared data, query results, we can access the cloud and get the results. And so this is the privacy-aware, policy-based quantified self-manager. And so what we are saying is data collection, data storage and access, data analytics, data sharing, every activity should be guided by policies. So you cannot collect data that violates the policies. So policies are key for building this data management framework. Okay, this is what we are developing. So policy-aware data collection, storage, access, analytics, learning, and sharing. So this is what our device data management framework and the cloud to store some of the data. So as more data are collected, the storage on the device will not be sufficient to store all of the data. So some of the data has to be pushed into the cloud. And again, based on access control policies, what sort of access for the local apps. So local applications running on the device will be given access to some of the data. And when needed, these apps will be allowed to access some of the encrypted data stored in the cloud through some very simple interface. In some cases, we may not really need to store. So if you're 20 years old, you don't have to weigh yourself every day, right? But if you are 60, 70, then you should weigh yourself. So because you don't want to really sort of clog the storage. So in some cases, data may have to be deleted to preserve privacy. So that's again a challenge. When you say data deleted, right? What does that really mean, right? If it's a physical object, you can just trash it. But if it's data, you delete it, and then you may need accountability and audit policies. So policies have to govern the data deletion process. We envision that data sharing and analytics will be carried out using the services running in the cloud. And again, based on different scenarios, some of the data could be sent without any modification. Some will be sent after sanitization, randomized response-based techniques to hide users, true response. And so some would be encrypted, some data not encrypted. Everything has to be, every action has to be governed by policies. Okay, so that is privacy-aware quantified self, right? A privacy-aware work. The second topic I said, data science for cybersecurity applications. And what we are focusing on, big data stream classification with Professor Latifa Khan, my colleague. So typically you use past, right? The past data to build classification model, predict the labels of future instances using the model, and it helps with decision making. So what I'm saying here is not, nothing new. This has been done for about what, 25, 30 years, build a classification model and classify yes, no. But that's not the main problem, because we have got big data, massive amounts of data arriving in real time. It could be stock market data, or it could be network traffic. So it's continuously arriving. If it's stock market data, concepts are changing. Today, it could be by Microsoft. Tomorrow, it's by Apple, then by Google, then by Facebook, and then by Amazon, right? It's continuously changing. See, those days, back in the 1990s and early 2000s, we were not able to do real-time data mining or real-time machine learning, right? The technology was not advanced enough. But now, with all these concepts changing, we are developing not just one classification model, and you will see in the next chart, we are building an ensemble of classification models, a collection of models. But then if data is infinite, right? So it's big data streams. What does that mean? Continuous flow of data, very common in our connected digital world, have massive amounts of data. And so we have this classification model. So we build a collection of models, right? And these models, again, the patterns are changing, but you can't have some of the outdated models. So what happens now? These models are talking to each other, communicating, and then throwing away the models that are no longer relevant, right? All models are thrown away. So we have an ensemble of models and we update the models. So if it's when the test data comes in, you test. If it's attack traffic, you block and quarantine. Benign traffic, you store. But then you continuously update the models. We actually a model update. You can have a human in the loop, but the models themselves may talk to each other and update and throw away the old model. So that's the whole idea. And this was joint work with Professor J.W. Hahn at University of Illinois, Urbana-Champaign. And we also have a patent based on this work. Okay, so we applied that, Dr. Khan, myself with our PhD student, insider threat detection. So there could be bad people pretending to be good, right? So this happens, like CIA has got, there's espionage. There are people sending secrets to the Soviet Union or adversary countries. And so that's not just humans. Okay, it happens with humans, but it's also happening with processes. So you can see processes that may sound like a database application or some email, or it could be some legitimate process, but it's actually a malicious process pretending to be good. So what did we do, right? We have to detect these anomalies. So we have designed and developed an ensemble-based, again, remember, collection of models, stream mining algorithms based on supervised learning that addresses this challenge by maintaining an evolving collection of multiple models. Models are evolving for classified dynamic data, and streams are unbounded length. The resulting classifier exhibits substantially increased classification accuracy for real insider threat streams relative to traditional supervised learning. So we have traditional support vector machine, and we used a one-class support vector machine and other single model approaches. But we have also designed and developed unsupervised ensemble-based learning. So we look at all of the different words and strings and patterns and all kinds of stuff, but we compress them because we cannot check everything. So we compress them and use some particular algorithm to encapsulate some of the strings into larger strings. And so and then we sort of identify anomalies. So unsupervised learning, compression-based techniques are used to model common behavior sequences. And so what happens? It results in a classifier, and this classifier exhibits substantial increase in classification accuracy. So we found unsupervised actually has better accuracy. So ensemble of classifiers allows the unsupervised approach to outperform traditional static learning approaches and boost the effectiveness over supervised learning approaches. So we compared both unsupervised and supervised learning. Okay, so this is our architecture. So we have all of these system calls, and we have got I chunks, right? K chunk, Ki. So I chunks, all the system calls are generated. And then, of course, we gather the data from chunk I. We have already developed a model up to chunk I+1. And so we extract features, learn, we apply unsupervised. It's a graph-based GBAD, graph-based algorithm. And we have a supervised one-class support vector machine. We have an ensemble of models, ensemble-based analytics, right? And so this is what we do. So when the models are old, we throw away. And then when the I+1 chunk arrives, same thing, we extract features, test data from chunk I+1, and is it an anomaly? Okay, so this was really a very interesting piece of work that we carried out and published a number of papers. And I believe that we also included some of the work. So we also publish our research papers. We put it together with some additional materials. We've also published a series of books that we use as reference books for our students. So this has been really, we wrote our last book was, we are working on another book on secure data science, but our previous book was on evolving insider threat. So it's actually big data analytics with applications in insider threat detection. Okay, so that finishes data science for cybersecurity. Now comes the dreaded part. What happens if your machine learning techniques are attacked, right? And we are using machine learning for almost everything, not only for cybersecurity, for healthcare, for finance, for retail, for marketing, for transportation, for almost everything. So remember, the adversary is very, very sharp and clever. Adversary is modifying the data. So adversary is learning everything what we are doing. So the adversary modifies the data to defeat our learning algorithms, right? So that's adversarial learning. It's not concept drift, changing concepts. It's not online learning. Adversary adapts to avoid being detected during training time, during data poisoning, during testing time, modifying the features when data mining is deployed. So essentially it becomes a game between us and the adversary, data miner and the adversary, because the adversary is trying to modify our approach and our learning. We then catch on to the adversary, what the adversary is up to. So we try to thwart the adversary. So see what happens. This is a support vector machine boundary line. The red squares are the bad instances and the blue circles are the good instances. And so what the adversary is trying to do is to push the bad instances into the good instances so it would not be caught. Okay, so what do? Before I tell you what we do, we look at the type of attacks. So our KDD, we published this paper in Knowledge Discovery in Database Conference. So we looked at two types of attacks. The free range attack is where the adversary can move the malicious data anywhere in the domain. So there's really a range from lower bound and the upper bound. And so I'm not going to explain all of this math behind it. So a paper provides all the details. So that's the free range attack. And other models are targeted attack. Adversary can move the malicious data closer to the target point. But remember, these are not the only two attacks. There could be numerous attacks, right? And so our approach is handling only certain types of attacks. So in reality, we need to really handle all of the attacks, and that's going to be it's a huge challenge. Okay, so now we come to our approach. So our threat model test time, deployment time attacks. Attacker modifies X to X prime. Modify packet length by adding dummy bytes, add good word to spam email, add noise to an image. So you've got here positive, the crosses are positive, the red are sort of bad instances, the green circles are good instances. This is our support vector machine boundary. Black dashed line is a standard support vector machine classification boundary, and the blue line is our adversarial support vector machine. So what we are trying to do is to move the dashed line to this blue line, but we don't magically create the blue line. There's a lot of mathematical computations go into that, right? So see, by moving this line, we have detected quite a few of the red crosses, right? And so this picture shows more clearly. So you can, and we show it in black, some of the additional things that we catch by moving this line. Now, you could ask the question, why not move this line right here? Then we can catch all the bad guys. But remember, if we move the line here, then our green circles, the good instances, will be shown as bad instances. And we do not want false positives, nor do we want false negatives. So paper was published, my colleague, Dr. Kantajulu, and his research scientist, Dr. Zhao, and Dr. Ji from Purdue. So it's a joint work funded by the Army, published in KDD conference. And so this was one of the early works on adversarial machine learning. Okay, now this is sort of a new area, trustworthy machine learning. Now there are two types, right? One question is, why do you want to do things in software? Why not use hardware to execute the machine learning algorithm sort of in a secure enclave? So computations over big data may require massive computational resources, and we may have to outsource it to third-party service. And so whenever you send the data out, it's not secure, right? So you could have untrusted environments, man in the middle, transmission, or inside a threat from adversaries. So we are conducting research in using hardware. So Intel has come up with secure encrypted data stream processing and trustworthy analytics using advancements in embedded hardware technology like Intel SGX to support trusted execution environment. Okay, so this is right to support trusted execution environments. So this, and I'm going to show you the picture, but recently so this is what we have been doing for a while, but more recently I was on a panel, and there was this very brilliant lady from University of Oxford. Her name is, Sadie, I think Sadie Crease, right? She's a brilliant lady. She is looking at applying formal verification. She's one of the experts in formal verification, and she's applying formal verification techniques for deep learning and machine learning. And so we really need to spend more time on looking at formal verification, applying logic for verification. So that's a sort of really a big emerging area where theoretical computer scientists and logicians can work with computer scientists, machine learning to develop formal methods. So the trusted SGX. So this is sort of the SGX design of the SGX. So you've got the application memory, runtime library, wrappers, encrypted code, and so on. And here you have the enclave, SGX enclave memory to carry out the data analytics, right? It's being carried out in secure locations. So you want to execute the security critical functions in some secure SGX enclave memory. Now, recently there have been some articles on some issues with SGX, so we are looking into it, but at least we had some very good results and published a number of papers. Okay, so now I finished part one. So we move on to part two. I'm keeping track of the time. So we move on to part two, security and privacy for Internet of Transportation and critical infrastructures. So we know Internet of Transportation. It's a type of Internet of Things. Internet of Things is exploding, right? From Internet of Things to Internet of Medical Things to Internet of Financial Things. So again, Internet of Things meaning for the house, for our home, clocks are connected to the Wi-Fi, to connected to our smartphones, to our coffee makers and tea makers, and our television and what we are purchasing, our emails and the whole lot. So everything is connected. Same way, transportation systems are connected. The trains connected to cars, cars connected to each other, the trucks connected to each other, to the roadworks. The whole idea is to make the experience, right, traveling experience as least complex as possible for the user, for the drivers, and for the passengers. And also we want communication, so we don't want delays, we don't want accidents. So that is the whole objective. Now, Internet of Transportation, it's an IoT for transportation, major impact on transportation industry. Autonomous vehicles aim to provide day-to-day activities such as delivering packages, improving traffic, the transportation of goods. In the US, trucks alone carry an estimated 63% of the freight of goods. Autonomous vehicles are not just limited to ground, right? We have air vehicles like drones and airplanes, and sea vehicles like ships and submarines and boats. Wide range of applications. So levels of automation for AVs range from 0 to 5, with current ground vehicles in the market having partial automation at level 2, and aerial vehicles having high level of automation at level 4, right? So we have AVs are ranging from 0 to 5. So companies are investing heavily in autonomous vehicles, right? GM spent $728 million in R&D in 2018, with plans of increasing to $1 billion in 2019. Okay, so 2019, of course, they did spend that much. I had to update it. I don't have the numbers for 2020. Why there is great potential in autonomous vehicles and the improvements it can do to the transportation industry. Security and privacy concerns pose new challenges that need to be addressed as we move forward. Okay. So, security of autonomous vehicles. AVs evaluate their environment using a variety of sensors: camera, GPS, inertial measurements unit, LIDAR, radar, ultrasonic sensors. So, number of components. Previous research has shown that sensors are susceptible to malicious tampering, IMUs are susceptible to sound waves, and GPS receptors are susceptible to spoofing signals. Vehicles should verify the veracity of sensor signals, right? So for instance, sensor-based, because they are not really, network traffic, right? Not zeros and ones. It's a sensor-based data. AVs rely on sensors to evaluate and interact with the environment. Inherited issues. Sensors are susceptible to GPS spoofing and transaction attacks that manipulate environmental physical signals, visual, sound, magnetic, and so on. Needed defenses. Classical computing security, such as memory protection, cryptography, and authentication, does not protect against these types of attacks, right? Classical computing security. Because, traditional memory protection and so on will not be applicable because it's all done real time. And again, no verification, because everything has to be done real time. AVs trust and act upon sensor data without any form of verification. But hopefully what I'm hoping is that the verification techniques could be enhanced so that we can develop some methods specifically for sensor data. Okay, so our approach, and this was led by Professor Alvaro Cardenas with our joint student, Professor Raul Quinones, physics-based anomaly detection, to build a reference monitor using a physics-based anomaly detection, PBAD. Reference monitor is a security kernel that enforces all the security policies. The algorithm will consist of multiple parts, right? So we are building a model offline of the AV's physical invariance, implementing an online tool to monitor expected and observed behavior to detect anomalies, okay? Raise an alarm if significant residual difference exists between executions, okay? So build a model offline, right, using AV invariance, and then implement an online tool, right, to monitor expected and observed behavior. And if anomaly, raise, right, so it's a 3-step process. Now, it was published in Usenet Security. Now, you should ask the question, so what is the big deal? You're talking about things that happened in, 10, 15, 20, 25 years ago. The big deal is developing the model, right? So offline pre-processing, the autonomous vehicles invariants are calculated using well-known linear model for aerial and ground vehicles. So you have the state, the input measurements, the pre-process sensor reading, the commands to rotors, predict states. So you have the XYZ axis, moments of inertia needed for nonlinear equations describing drone behavior, mass of vehicles, drag factor, thrust factor. Okay, online stage, an extended Kalman filter is used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. And then the algorithm is divided into two sections that predict and corrects the estimator before it compares. So we are using extended Kalman filter. Now, those of you who are electrical engineers, and I'm not an electrical engineer, I'm a computer scientist, Kalman filters have been used for years and years and years, especially control theorists, right? And control engineers, they use Kalman filters. So, but again, the whole challenge for us is to model the physical properties and applying the Kalman filters. And then anomaly detection, we use the CUSUM algorithm. It's already in the literature to detect the persistent attacks. Alarm is raised if residual difference is larger than a predefined threshold. Okay, so no AI here, no machine learning, no AI yet. So the physical implementation, we did it for aerial vehicles and land vehicles, not sea, because we are living in Dallas-Fort Worth. We don't have oceans, and of course we have lakes. But again, it was less difficult for us because we have drones. So we have aerial AV Intel ready to fly RTF drone, controller P times PX4 flight controller, focus on detecting for aerial GPS spoofing and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope attacks are detected after 1.5 seconds. Overhead introduced 5.4332, right? So we have these drones. So it's a 5%. Ground AVs, so we used built on top of Traxxas Ford Fiesta, Rally Chassé, controller ROS Kinetic Aim, focused on detecting visual attacks on the camera, attacks detected after 0.1 seconds. Overhead introduced is 2.25%. Okay, so ground vehicles, each threshold produces a probability of false alarms of approximately 2%. Okay, so this is what we have designed. It's 2% for ground and 5 point something percent for aerial vehicles, the physical implementation of this algorithm. Now, what about privacy? So much of the work on transportation security has been on security. But privacy is important because beyond the security of vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles, motion sensors, lampposts, surveillance cameras to help identify traffic jams, reroute vehicles, and increase vehicle safety. Okay, so we are applying so much of machine learning, and we'll see, for transportation, right? There's so much machine learning and AI and deep learning being applied for transportation security. So these machine learning techniques could be attacked. And not only that, the machine learning techniques, remember what I said earlier, you can put collections of data together and infer something that is highly private, right? So from a user's perspective, because of all these technologies, privacy concerns arise from all the information needed by such systems that could lead to private information being exposed, such as vehicle identification, driving patterns. Now, I don't want people to comment about my driving patterns, take photographs and so on and send it to my insurance company. Nor do I want people to find out that I'm smoking in my car. I don't know whether it's legal or not these days. Well, I don't smoke, of course. Or drink alcohol. Well, I don't drink also. I don't drink alcohol, but still, right? People could be doing that. But that's my privacy of my own car, although I shouldn't say that's privacy because it's privacy of your own home. Once you leave your house, forget about privacy, right? So, because when you are driving, right, you have to think about the other folks. But in any case, sometimes, we may not, certain things we may not want people to know. So that's why privacy is important. Again, policy aware. So somebody cannot collect data. So we need to have appropriate policies. So legislators, engineers, scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. This will aid at improving the public perception, reduce hesitation from customers, and increase the adoption rate of new technologies. So part 3 is applications of security and AI. So essentially part 1 to part 2, which is Internet of Transportation and Infrastructures. One thing I want to tell you all about policies, we computer scientists, we talk about policies, but they are really like toy, T-O-Y policies. So our policies are like, John is telling Mary, I will tell you a secret, but do not tell Jane, right? That's like little children. But we are working with real policy experts. Our dean of our School of Economics, Policy, and Political Sciences, she's very well known. Dr. Jennifer Holmes. She is a top policy expert. So we work with her on policies. And so for me, I have to sort of have an understanding, right? So what I'm doing now is doing a public policy certificate a public policy analysis certificate at the London School of Economics. So I started like what, 3 months ago, and I'm finishing in 2 months. So I'm really, I'm sort of more than halfway through. Remember, learning is a lifelong process. So I'm really enjoying doing, policy. So I'm beginning to understand what these policies are all about. How do you set policy agendas? And how do you implement the policies? How do you evaluate the policies? So I'm getting a much better understanding and appreciation of policies. Anyway, so now let's go to part 3. I have only 3 charts. So data science for transportation security, right? That's the first one. So we said data science for so cybersecurity, like intrusion detection or malware analysis. But for transportation, Internet of Transportation systems, we know, are subject to attacks. Like any cyber physical system, streaming data is being collected from systems, including autonomous, and in the future, of course, driverless vehicles could be a disaster. As transportation systems go electric, we need energy conservation. Threats to the security of such systems could cause massive damage, including accidents, loss of lives, as well as stranded on lonely highways due to attacks on energy management, right? So there could be massive problems. Because it could, that there could be hackers could be attacking our energy systems, our gasoline, it could show different readings, and readings could be manipulated. So data science ML techniques are being applied to analyze the data. So my question is, can the stream analytics learning, what we discussed earlier, can be that we have developed, say, for financial data, stock market data, network analysis, network attack data, can we apply for the transportation data? So for this, we need to understand the transportation data. What is the structure of the data? So the main question is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data being collected. Okay, the second topic is adversarial machine learning. What is that? Our Internet of Transportation systems will depend heavily on data science AI ML techniques for various applications, including optimum directions, driving without a human in the loop. So machine learning techniques, without a doubt, right, it's being applied for transportation systems. So the adversary will be learning the models used by the vehicles, as well as learn about the data used in the training of the models, right? So adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms have to adapt to thwart the adversary's actions, right? Eventually, it becomes game playing between the adversary and the vehicle's machine learning algorithms, right? So it's a game that is being played. And so, just like I mentioned earlier, what is this game, right? Is it zero sum? Is it Bayesian? Is it Stackelberg? So we need to have a good understanding of the data. And research on this topic is only beginning. Okay, it's adversarial machine learning. So remember I showed you privacy-aware policy-based data management framework for quantified self. Similarly, can we have a privacy-aware policy-based data management framework for Internet of Transportation? But instead of healthcare data, social media data, and so on, we have radar, GPS, cameras, LIDAR, ultrasonic sensors, and there's a collection device inside the car. So we have some sort of like a smartphone-like device, data collection, data storage, data analytics, and data sharing. And some of the data in the cloud and through cloud-based services, some data could be encrypted. And what we are developing is a privacy-aware, policy-based autonomous vehicle. So what we are saying is policies have to guide everything: data collection, storage, analytics, and sharing. Okay, so we haven't developed this yet, and this is going to be the future. So what are the directions? Summary and direction. So developments in integrating cybersecurity and AI, data mining exploding, right? We talked about it. Applications of AI for security, insider threat, and security for AI, adversarial machine learning. So 2 things we discussed. Then I also talked about privacy-aware healthcare and managing one's life activity, right? Privacy-aware quantified self. I said it has to be policy-based. At the same time, there is work now on Internet of Transportation, Internet of Things, and infrastructures. Security and privacy solutions are being developed, mainly physics-based solutions. As driverless cars become a reality, more and more of the AVs will use AI ML techniques. How can we develop AI solutions for detecting malware in AV systems? And how can adversarial machine learning work in AV systems? Okay, so we have, so we are developing AI solutions for detecting malware in AV systems. So how can adversarial machine learning work? Can we develop a privacy-aware, policy-based data management framework for Internet of Transportation and infrastructures? Okay, so that's the question I asked. And is it possible to perform trustworthy machine learning analytics efficiently when so much of data is coming from all directions? Okay, we talked about Intel SGX chip, but there's also formal verification methods, right? So that's, I think, is going to really take on, because that's one of the ways that we can have all these machine learning algorithms and the deep learning algorithms secure. And so there are numerous opportunities for substantial research and development. Okay, so this finishes the presentation. As I said, we've got all our email addresses. Please feel free to contact any of us. And let's see. So at this time, I'm going to stop sharing. And so the question then is, right, so I'm open to questions. So what I'm, sorry about this, I know some notices, right. So the main points that I want to mention is that without a doubt, right, AI is exploding. And so AI, data science, machine learning, big data. And so what I'm saying is we need to take advantage. And so all of these AI techniques, machine learning could be applied for cybersecurity applications. But these AI techniques are, right, could be attacked. So we have all this adversarial machine learning. But because of AI and machine learning, data mining, we can put things together and infer something that is highly private. So you've got privacy-aware data management, policy-aware data management, right? So privacy. So policies have to govern. Part 2 was on Internet of Transportation. And so I talked about some very simple things, applying Kalman filters for anomaly detection. But again, the modeling part is very, very challenging. So that's really, quite hard. The modeling of the cyber physical system. So we had some good results. We did for aerial vehicles and also for land vehicles, but we haven't done anything for sea yet, for oceans, like ships and submarines and so on. Okay, then we applied part 1 to part 2, and that was the future, right? Future, how can we apply machine learning for Internet of Transportation? What happens if those machine learning techniques are attacked? And then privacy-aware, policy-based transportation, Internet of Transportation system. But then one of the things I'm stressing is trustworthy analytics, right? We can do some of the things in hardware, like the Intel SGX chip, Intel SGX platform, where we can execute the machine learning algorithms in these secure enclaves. But we have to also think about formal verification methods for deep learning and AI. That means, how do you take some of the formal verification methods and the logic-based methods that have been developed, specify specifications, formal specifications and formal verifications for these machine learning algorithms. And I believe that that could be one of the promising approaches for the future. And with that, I'm going to end my presentation. And again, I'm looking forward to giving this presentation live tomorrow morning. It's actually past midnight now. So it's going to be, remember, 1 p.m. Eastern Daylight Time. And that's going to be at the New York Institute of Technology. It's just a wonderful location. It's on Columbus Circle. Unfortunately, I'm here home in Dallas will be giving this invited presentation. But that real part, that particular spot, where NYIT, the Manhattan campus, it's on Columbus Circle. That's just one of the most, I would say, sort of most wonderful locations, I would say, in the United States. So I'm really looking forward to giving the presentation, although it's virtual, but still, I can sort of imagine that I'm, giving this presentation. I'm in Columbus Circle in New York City, in Manhattan, and giving this presentation. And again, thank you very much.